Today we are going to discuss about the Gaussian or the normal distribution. I am Dr. Abhishek Joshi and I will be discussing about the Gaussian distribution. We will define the Gaussian distribution first and then finally we will solve the numerical based on the Gaussian distribution. So, this is the topic of our syllabus, digital communication KEC 601. So, what is the Gaussian distribution? The Gaussian random variable, because earlier also we are discussing about random variables, the cumulative distribution, the probability density function. So, what is the Gaussian distribution for a random variable x, where the value of x lies between minus infinity to plus infinity. So, we have the random variable whose value is lying between x lying between minus infinity to plus infinity. So, for this random variable, x, we are defining the Gaussian random variable for the PDF, that is a probability density function, that is p of x is equals to 1 by under root of 2 pi sigma square exponential minus x minus m by 2 sigma square and x minus m whole square. So, what is m? M is nothing but the mean of the variable or mean of the random variable. And what is sigma? Sigma is nothing but the variance. Okay. So, we have the standard deviation, you can say sigma, and is sigma square we are using. So, it is a variance, and we have this x minus m by 2 sigma square. So, this is the complete definition for Gaussian distribution. Now, we can relate this Gaussian, or we can define the standard or the Gaussian which has the 0 mean and unit variance. So, if we substitute the mean here, because m is nothing but the mean, which is which we have already defined as expectation of x. Okay. So, here m is nothing but expectation of x. Okay. And standard deviation we have already discussed in our previous lecture. You can refer my previous lectures to define the standard deviation. Okay. So, I am not repeating it again in this lecture, you can refer it. So, we have the standard normal or the Gaussian distribution which have the 0 mean. So, what is the value of m here? In case of a standard distribution, m will be 0. And what is the value of the variance? It is equals to sigma x square is equals to 1. Okay. So, we have the value m equals to 0 and sigma square is 1. So, we have this given by 1 upon under root 2 pi exponential x square by 2. Why we are getting this? We have substituted the value, that is m equals to 0, sigma square is 1. So, we are getting this. Now, the CDF, the cumulative distribution function. Now, we have defined the PDF. Now, what is the CDF for the Gaussian distribution? So, in case of the CDF, we note this CDF by capital F of x, because x is random variable, and for this case we have the CDF given by 1 upon 2 pi, because we know that it is nothing but integration of the probability. So, we have integrated for the limit minus infinity to x exponential minus x square by 2 d of x. Okay. So, this is the CDF of the Gaussian distribution, or you can say the normal distribution. So, interchangeably we can use either normal distribution or the Gaussian distribution, we can use any one. So, we have this Gaussian distribution, that is a probability which is given by the curve, or it is known as the bell shaped curve. We can call it as a bell shaped curve. So, because this resembles to the shape of the bell, so we are calling it as the bell shaped curve, having the value, the maximum value given by 1 upon under root 2 pi sigma. This is the maximum value of this bell shaped curve. And what is the mean? Mean is the center of this bell. The center of the bell is the mean of the curve, which is given by m. So, when m equals to 0, this means this curve will be shifted to the value 0. Okay. So, if I want to plot the Gaussian distribution with m equals to 0, or if I want to plot the standard distribution, standard Gaussian distribution, so how I can plot it? I will simply shift this curve at the center. So, what curve I will get? I will get the curve like this, where this center is m equals to 0. So, mean will be 0 when this curve will be centered, or this bell is centered at m equals to 0. Okay. So, this is the standard Gaussian distribution, and this is the Gaussian distribution which have some value of mean, okay, which is given by m. Now, the cumulative distribution function. How we can plot the cumulative distribution function for a Gaussian distribution? We have the cumulative distribution function for a Gaussian. It is given by this shape of curve, having the minimum value is, it starts when we talk about minus infinity, it starts from 0 and it reaches the maximum value, that is 1. And this is the property of the cumulative distribution function, that at infinity, at x equals to infinity, you will get the maximum value, because this is nothing but the maximum value of the probability. Okay. The same we are calling it as, and the mean, as you can see, at a value m, it is equals to 1 by 2. So, we are using these value interchangeably while solving the numerical. So, we must remember the shape of the curve, and if we want to find the area under the curve, we must know that what shape, or whether we are using a standard distribution, a standard Gaussian distribution, or we are using a Gaussian distribution which have the value of some mean or the variance. Okay. So, we have to keep in mind while solving the numerical. So, we have shown the PDF and the CDF of the Gaussian random variable x. Okay. Now, the function that is closely related to the Gaussian random variable, that is a Q function. So, Q function, how to define the Q function? What is the Q function? So, Q function we can define a Q function, that is Q of x. Again, it is a random variable x, which is nothing but the probability for the standard distribution where we have the mean, that is m, it is given by m comma sigma. So, value of the mean is equals to 0 and the standard deviation is equals to 1. So, we have the value of sigma as 1 and m equals to 0. So, sigma is 1, m is 0. Okay. So, when we are taking this standard distribution, then we have it is greater than equals greater than x. So, how to denote it? So, we can write this is nothing but 1 upon under root 2 pi integration from x to infinity exponential of minus t square by 2 dt. So, we are getting this Gaussian distribution. Okay. So, the Gaussian distribution, that is a CDF of a Gaussian random variable, is given by f of x, that is capital F of x, and we know that it is nothing but the integration from minus infinity to x 1 upon under root 2 pi sigma exponential minus t minus m. We have interchanged the variable here, that is t. So, t minus m by 2 sigma square, and m is the mean and sigma is the standard deviation dt. So, that is equals to 1 minus, so we can write is nothing but the integration from x equals to x to infinity 1 upon 2 pi sigma square exponential of t minus m by sigma square dt. So, that is equals to, for the solving it, we are getting 1 minus integration. So, we have interchanged the limit, that is t minus m by sigma we have substituted here in this expression, and we are getting 1 upon under root 2 pi exponential of minus x square by 2 du, because we have substituted here the value of u, that is equals to t minus m by sigma. So, while substituting it, we are getting this expression. Okay. So, we can relate this is nothing but the q function. So, this is nothing but the q function of the u. because it is an integration with respect to u. So we have the q function as 1 minus of q u, that is x minus m by sigma, or you can write t minus m by sigma. So we have interchanged it. So we have this q of u here. So we can write the change of the variable, that is u is equals to t minus m by sigma. And what is the plot for the q function? The q function can be plotted for the different values, having the maximum value as 0.5 here. So it is nothing but 1 by exponential of minus x square by 2, or we can write it as 1 upon x under root 2 and exponential of minus x square by 2. This is nothing but the q function, and we have the whole expression, which is x by 1 upon x 1 plus x square under root 2, that is exponential of minus x square by 2. So this is the plot for the q function. So you can refer this plot for the different values of x for a q function. So what is the properties for the q function? Again and again we are discussing about the q function and its properties. The properties for the q function having the values that if we have the q of x, if we are solving for the value of x, and if x equals to 0. So if x equals to 0, then the value of the q function will be equals to 1 by 2. As we can see from this curve also, if you are using the variable, okay, you are denoting it by q of y, we can use any variable. So we have used here qy. So in our figure we can see that what is the value of q of y at x equals to 0. So if you see the x equals to 0 here, you can see that the value is 0.5. So the value is 0.5. Okay, so value of qy is 0.5. So we are writing that at x equals to 0, that the value of the q function is equals to 1 by 2. Okay. Similarly, at x equals to infinity, so at x equals to infinity or y equals to infinity, if you are using the variable y, you whatever variable you want to denote, you can use accordingly. So if you are using the value that is infinity, then the value of the q function for x equals to infinity is 0. As you can see in this curve also, this curve is falling down and it is going to 0 at the value infinity. Okay, that is it. So what is the value at x equals to or y equals to minus infinity? So what is the value of the q function? The value of the q function at x equals to minus infinity is the maximum value, that is 1. And next property is the q function for a value, negative value of x is equals to the q function 1 minus the q function that is a positive value of x. This means if you are taking the q function for minus 1, so you can write it as 1 minus q function of the positive value, that is 1 here. Okay. So accordingly you can write, or you can write if you have the negative value of 0.7, okay, for an example, you can write it as 1 minus the q function of 0.7. So if you have any value negative or positive, you can use the same table of the q function to find the negative or the positive value, because in the table you will get the positive values, and if you want to find for the negative values, you can refer the same table by subtracting it. Okay. So we have the CDF, that is a cumulative distribution function. There is a PDF for the standard or the normal distribution function. As you can see here, the mean is centered, that is mean is equals to 0 here. So this bell curve is centered at m equals to 0, and the area under the curve for q of y, you can see here, if y you have the value y here, then the area under the curve means you will get this region. Okay. So q of y will give you this region for a given value of y. So if you have the value at a particular point, then it means that for a bell shaped curve, or if you are plotting the PDF, then this q of y is nothing but the greater value. Okay. Now we will see in this numerical how to solve it. Further we will use this numerical to solve it. Okay. So this is the table for the Q function. As you can see the table, the value at x equals to 0. So what is the value at x equals to 0? According to the curve also it is matching, that is 0.5. Similarly it is decreasing because we have seen the curve, it is just like this. Okay. So this curve we have q of x, it's like this, and at x equals to 0 we have the value 0.5 or 1 by 2, we have seen in our previous slide. So as you can see for 0.1, 0.2 the value is decreasing, so accordingly the values are decreasing, and we know that at x equals to minus infinity the maximum value we are getting, that is 1. So at x equals to minus infinity we have the value 1 here. Since the bell shaped curve is symmetrical in nature, so that's why the bell shaped curve, so we can divide this bell shaped curve in the two halves. The maximum area which is covered by this bell shaped curve, which is equals to 1. So the area under the curve is 1. So if we want to divide this bell shape, so we can divide this bell shape in two halves. How we can divide? So if we take this center line and we are dividing this curve, so the area under the curve covered by this curve is 0.5, and for the positive region again this area will be 0.5. So again we can divide, because according to the definition of probability the value, maximum value is 1, but this bell shaped curve we can divide into two equal halves, that is 0.5 and 0.5, because it is symmetrical in nature. So in numericals also we must remember this property, because again and again we can use this property to solve the numerical. So now you can see the values, how these values are decreasing for 0.5, 0.6, and it is rising from 0 to the value that is 7.1. So after 7.1 you can see the value is very small, that is 6.23 into 10 to the power minus 13. So you can refer this table of Q function, which is easily available on internet as well. So you can refer this values, and for a given value of x you can find the value for the Q function of x. So we have the Q function relation with the ERF, that is the error function. So how we can relate the Q function with the error function, because in communication again and again we are using the error function, the complementary error function. The complementary error function is given by ERFC of x. So ERFC of x is nothing but 2 by under root of pi integration from x to infinity and exponential of minus y square dy is, that is equals to. So this is the relation of the complementary error function. The complementary error function we have 2 times of the Q function x by x under root 2. So this is the relation, and this Q function for the random variable x is equals to 1 upon 1 by 2, that complementary error function ERFC x by under root 2, that is equals to 1 by 2 1 minus ERF x by under root 2. So this is the relation between the Q function and the error function, that is ERF and the complementary error function, that is ERFC. Okay. So we are taking one numerical based on this. So one numerical is there. So we know that if the height of the number of base stations are given, base station antennas, we have 300 antennas, 300 base station antennas are normally distributed with a mean height. You can say the mean height is given by 64.5 inches, and because the height is given as 64.5 inches, and the standard deviation of these antennas are having 3.3 inches of height. So how many antennas are having the height less than 5 feet? So we have to find the number of antennas that have the height that is less than 5 feet. So what we have to find? First we have to find the probability for x is less than 5 feet. 5 feet in terms of inches, it will be 12 5 is 60, because in 1 feet we have 12 inches, so it is 60. So what we have to find? We have to find the probability for x is less than 60. So how to solve it? So we will solve probability that x is less than 60. So before that, we must remember what for the q function we must find x minus m by sigma. So x minus m by sigma. So first we have to find, this is nothing but x minus m by sigma. So here x is a random variable, so we are not substituting any value right now. So what is the value of mean? So mean is given by 64.5 inches. So mean is, value of m is 64.5 inches. Okay. And what is the value of the standard deviation? Standard deviation is given by 3.3. So sigma is 3.3. So we have the value of m, we have the value of sigma. So substituting it, we are getting x minus m means 64.5 by sigma is 3.3. So further solving it, so what is the value of x here? So for the particular value of x, we have the x should be less than 60. So if we substitute, this means what we have to find? We have to find the if we denote it by some variable z. So what we are finding? We are finding that the probability that z is less than x minus mu by m. So that is, what is the value of x here? That is 60 minus 64.5 by 3.3. So what we have to find? We have to find the probability for z. We have denoted it by variable z. You can use t, z, whatever variable you want, less than. So if you solve it, you are getting 1.36. Okay. So we have to find the probability for z is less than 1.36. But we know that it is nothing but the q function. The q function, and it is minus 1.3, sorry for that, it is minus 1.36. So we are getting minus 1.36 because we have the negative value greater here. So minus 64.5, so minus 1.36 you will get. So for this particular value, this is nothing but the q function of the value, that is, because it is less than 1.36, so we can find for the greater. So q value 1.36. Now what is the value of q function for 1.36? So we will refer the table for that. So table is given here. So we will see the value of x in this table. So the value of x is 1.36. So we can see here we are getting 1.3, here we are getting 1.4. So detailed tables are also available on net. This is the summarized table. Just to explain you, I have used the summarized table for that. So we have to use 1.36. So here we are having the value 1.3 and 1.4. So this value is approximately between these two values. So we have at 1.3 we have 0.096 and 1.4 we have 0.080. So it's intermediate between these two values. So we can use 0.089. So if we are using this value 0.089, that is 0.089. Okay. So if you are using this 0.089 value, so this is nothing but the probability that is having x is less than 60. Okay. So probability that x is less than 60 is, we are getting this value, that is the probability that x is less than 60 is equals to 0.089. Okay. So we are having this value 0.089. So what we have to find? We have to find the how many antennas are having the height less than 5 feet. So how many antennas are there? So for that number we have to multiply with the total number. So total number is 300. So probability we have to multiply with the total number. So 300 multiply with the probability, that is 0.089. So if you solve this, so how many antennas will be there? It is approximately 26.07. So we are getting 26.07. So we can approximate it as, so number of antennas that is having this height, that is equals to 26. So we can use this Q function to find the, or to solve these types of numerical of the Gaussian distribution, because it's written that it's following the normally distributed curve. So that's why we have used the technique of the Gaussian distribution to solve these types of numericals. So in our today's lecture, we have solved, we have discussed about the Gaussian distribution, then we have solved one numerical based on this. So Gaussian distribution is clear, and earlier we have, in our earlier lecture, we have discussed about the exponential distribution. So here we are going to stop our lecture. Thank you.